see.
Right. So, yeah, I mean, basically our lab is following. We sort of follow what they have done, but engineering it, right, to tailor the technology to our need for years. Yeah, and that setup is actually, I think we copied and modified a little bit from Göttingen's max Institute. So with that, right, we can reach the super resolutions. The working principle was actually quite. This is traditional. Right, traditional. Yeah, oh, this is fine. Yeah, fine. So what you can see is that before the stimulus emissions, right? Before the stimulus emission, you can see it's diffraction limited, right? Like what we see in the astronomy or microscope. But once you turn on the beam, which is donor beams, right? And the donor beam will just inhibit or deplete the molecule that will give out fluorescence. So you are left with the one in the centers, right? And then by detecting the fluorescence just from the center, we can break the diffraction limit.
Well, I guess a factor of 3 or 4 or something like that.
Actually, depends. I mean, what we have demonstrated here is only a factor of 3 or 4. But the base record depends on the protocol you use, laser power and so on. Right now they can reach 8 nanometers. Right, compared with diffraction limit, which is usually maybe 200 nanometers. Right, they can reach maybe 25 times bigger.
Wow. That's impressive. So you're using this this is being used for biological studies.
Well, this one is not used in biology yet. This is still on the physics side.
Okay.
Right, and we are trying to know what's going on with stimulus emissions. This stimulus emission has many interesting properties. Right, it's like when we see the light, excitation, fluorescence just goes out anyway. But stimulus emission allows you to read the signal out. Right, I mean, you collect the molecule which is supposed to give fluorescence. You can deplete it, meaning that you are reading the signal out. Right, and then meaning that you are turning an incoherent process into a coherent process. Right, and then extract something out. Right. So together with locking detection and this, they have this new method of stimulus emission microscopy, stimulus emissions. Right, and then once you can read out in a certain way, meaning that I don't need a huge NA to collect the signal. Right, I can collect the signal in the right direction always. Right, so it's very strange thing that nobody's, I mean, stimulus emission has been around for so many years, but nobody's sort of using it as a tool to do it real now.
What does it mean by subdifraction?
Meaning that the resolution go over the diffraction limit.
It looks very simple, but this stuff is very.
Right.
Putting this together is complicated, I'm sure.
Well, basically we need to reach nanometer stabilities, right? Because if you have a resolution, say 30 nanometers, right? Curve of pins or anything, right? Just kind of resolutions, right? So it's like high resolution TEMs, right? You need to be in a very stable foundation of ground, right? Otherwise, it's just a vibration to kill everything.
So we're down in the basement, is that right?
Yes, right, in the basement.
And then you hope there are no subways close to you, I guess.
I think it's fine now. Right, that's one thing. And second thing is that the air table, right, air table, if we do a 2-layer of air table, usually is good enough to give us this nanometer stabilities.
But this looks like a single layer.
There's another layer here.
Oh, I see.
Right, there's another one here. Right. Well, we should insert this rubber in. Right now they are doing alignment, so they can be hands. Impressive. Right, yeah. One layer and another one.
So what's inside this box?
Detectors.
Okay.
It's detectors. So
And what wavelength is all this done at?
It's all optical wavelengths.
Okay,
Right, it's optical wavelengths. And, this is a
Green?
near IR.
IR?
Yeah, near
Oh,
IR.
I see, okay.
Right, 800 nanometers.
Okay.
Right. Yeah, this is W 800 nanometers. 才15 wavelengths.
哦，
你那个 continuum 有拍吗？
没有诶，因为今天是